So dilations. We're going to go over some basic information today, and then we'll spend more time and go into more detail on Monday. Okay. Who can tell me though what a dilation is? What do you know about dilations? Jacob.
I'm pretty sure it can either shrink in size or it can grow.
Okay, so it's a figure that either can get bigger or smaller. Okay. Now let me give you the formal definition. So a dilation is a transformation, and you talked about transformations in IM1. Who remembers what some of the transformations are?
It's adding, I believe it would be something like 2 plus to the current point. It's adding to a point, whatever is to the x value.
Okay, so that's a translation where we add something to a current value and it just moves. So you have translations, rotations, reflections. Those are all types of transformations. Dilation is a transformation as well. Okay, so it's a transformation that can change the size of a polygon, but leaves the shape unchanged. So if I have a square, I can do a dilation and my square can get larger or smaller, but it's still going to be a square. You're not going to go from a square to a triangle. Okay? Your figure stays the shape of it stays the same. It's just going to get bigger or smaller. Okay? Now, in order to perform a dilation, we have to use something called a scale factor. Okay, so to perform a dilation, we have to use something called a scale factor. And here's where yesterday's lesson plays in. So a scale factor is the ratio of the lengths of corresponding sides in the image and the pre-image. Okay, so we're dealing with ratios. So a scale factor is the ratio of lengths of the corresponding sides in the image and the pre-image. The image is going to be your new figure. Okay, so after you perform the dilation, you're going to have your image. It's your new figure. The pre-image is your original figure. Okay, so we start with our pre-image, we perform a dilation, and now we have the image. So for instance, if I give you triangle ABC, and we perform a dilation, my image is going to be triangle A prime, B prime, C prime. Does that look familiar? Yeah? There's two types of scale factors that can occur. So if I have a scale factor that is greater than 1, what do you think is going to happen? If I perform a dilation with a scale factor greater than 1, what do you think is going to happen? What's going to happen to my figure? It's going to get bigger, which is known as an enlargement. If I have a scale factor between 0 and 1, my figure is going to get smaller. Does anyone know what that's called? It shrinks, yes. It's called a reduction. Okay, so you have enlargements and reductions. So again, if your scale factor is greater than 1, you're going to have an enlargement. If your scale factor is between 0 and 1, you're going to have a reduction. Now, there are some properties of dilations that we're going to talk about right now. They're going to be super important once we start dealing with numbers. I mean, they're important in general, but we're going to focus on these once we start adding numbers. So, properties of dilations. The first super important one is that we are going to preserve angle measure. So we're going to preserve angle measure. So for instance, if you have a square, what are the measures of the angles of a square? 90 degrees, right? Now whether that square gets larger or smaller, what are the angles of that square? 90 degrees. Because as soon as it's not 90 degrees, is it even a square? No. So the angle measures will always remain the same no matter what happens to your figure. Whether it gets smaller or larger, the angle measures will stay the same. Okay? We also have side lengths to deal with. And the side lengths are going to be proportional. Okay, so they're not going to be the same, they're going to be proportional. So back to our square example. If I have a square that initially has a side length of 5, and that square gets bigger, is it still going to have a side length of 5? No, it's going to have a bigger side length. It could be 10, but all the sides will now have a side length of 10. Okay, when we write a ratio, it's going to be proportional. So they're not going to be the same, they're going to be proportional. What is this symbol? Congruent. So all angles are going to be congruent, no matter what happens to our figure, whether it gets bigger or smaller. No other class knew this. Let's see if you know this symbol. Nice. Similar. Okay, all sides are going to be similar. They're not the same. They're similar to each other because they are proportional. Okay, so these two properties are going to be the biggest ones, the ones that we're going to focus on the most. But I do want to mention a third one. With a dilation, we are going to preserve orientation. So here's what that means. There are different types of transformations. We've already said we have rotations, reflections, translations, right? We have a dilation. So we could have a figure that gets smaller and moves somewhere on our graph. That's okay. What's not okay is for the letters to start switching places. And I'm going to show you an example in a second and you'll be able to see it. But you can't start with A and then have that switch places with where B was. That's not allowed. Okay? You can rotate your figure, but if you rotate it back, it's still in the same spot. Okay? So give me a second and I'll draw a picture and we'll see what that looks like. Questions, though, on all of our definitions and properties? Okay. In IM1, you talked about congruent triangles a lot, right? We're going to talk about similar here. So we are going to state the corresponding sides and angles. We're going to state the corresponding sides and angles. So I have triangle ABC for you and triangle DEF. Okay, that's the similar symbol. So one's probably bigger than the other. They're not congruent to each other. But based on our properties of a dilation, angles are congruent, sides are similar. This is called your similarity statement. You've seen that with the congruent symbol, right? Now the nice thing about a similarity statement is it tells you in that statement what pieces are congruent and what pieces are similar. So if I'm just dealing with angles, I can say angle A, and we're talking about congruent for angles. Angle A is congruent to angle D because A and D are located in the exact same spot. What if I said angle B? What would angle B be congruent to? E, because it's in the exact same spot. And then what's my last angle? C, and F. You'll also notice that I use the angle symbol. Okay, if you just give me a letter that's a point, we're not talking about the angles, so you need to make sure your notation's proper. Now, side lengths. AB is going to be similar, so AB would be similar to DE, right? Because AB are the first two letters, DE are the first two letters. So AB is similar to DE. And again, we're using similar in this case because the sides are not the same, they're proportional. What if I give you CB? What would CB be similar to? FE, good. You need to make sure you use the letters in the appropriate order. So since I went from the last letter to the middle, I have to go last letter to the middle. Anyone know what my last side length would be? AC and DF, good. So we can just use a similarity statement. We don't even have to have a picture, and we can tell what's congruent and what's similar.
As you got a message, you just keep beeping.
Questions on that? Okay, so let's look at a picture. So we want to determine if the transformation is a dilation. And we're going to explain why. Okay, so you have to bear with me for a second while I draw. This is just a sketch, so yours does not have to be perfect. Okay, you're just sketching for now. We're just doing some basics. So my question to you is, did a dilation occur? Okay, I heard yes from quite a few people. So here's my pre-image, here's my image, right? And it looks like my image is smaller. I agree with that. Does anybody see a problem? The letters, right, your angles aren't in the same spot. So it looks like it's a reflection, right? Remember what a reflection is, where it flips upside down? But if it flipped upside down, wouldn't B be down here?
Yeah.
Okay, so what happened? If you rotate it, that means A is going to be over here. So this is not a dilation. What did we not preserve? We did not preserve orientation. Good. So if B and C were flipped, you'd be fine. It would be a dilation, it would be a reflection. That's okay. But because B and C changed spots somehow, like they're just not in the same location, we didn't preserve orientation, so there's no dilation that happened. Okay? One more. Now, it's not necessarily drawn 100% to scale because I'm not a great drawer. But based on the information that we do know, would you say a dilation occurred? Yeah, right? Here's my image. My smaller figure is my image. My pre-image, excuse me. My smaller figure is the pre-image. And then my new figure just got bigger. But all of the letters, like everything where it started is still in the same spot. It just got bigger. Okay, so yes, this is a dilation. Yeah. Sure. I don't know. So the question was, will there ever be a reduction and then a reflection? Yes, that can absolutely happen. I don't know if we get that in depth. I think we just focus on dilations, but I don't remember, to be honest with you. All right, last thing I want to look at is how to find scale factor. It is the last problem, so if you're running out of room, just try to squeeze it somewhere. It's not going to take up a ton of space. So find the scale factor. And I'm going to give you your two figures, and I'm just going to give you the coordinates of those two figures. And above we learned that scale factor was a ratio, so we're going to write a ratio. But before I do that, let's kind of get some information. Which one is my image versus my pre-image? The one on the left is the pre-image. Right, so this one is the pre-image. Yes. Okay, because your primes are your image. Now, if you're looking for scale factor, it's a ratio. Our ratio is going to be our image over our pre-image. Okay, for scale factor, it's image over pre-image. This is important. Image over pre-image, so new over old. Now, you can use side links. Here we don't have side links, but we do have coordinates. So I'm going to look at, and I'll show you how it'll work with all of them, but we're just going to pick one. I'm going to look at the coordinates for A and A prime, and I'm just going to look at the X value. Okay, so the X value for A and A prime. What is the X value for the image, which is here? We're just looking at A. What's the X value for A prime? -4, right? What is the X value for A on my pre-image? -2. So I have a ratio of -2 or -4 over -2. That can be reduced to what? 2 over 1. Okay, so this right here is my scale factor. Now we said if a dilation happens, everything is proportional. So I should be able to take my scale factor and multiply it and get my new figure. So I should be able to multiply it by my pre-image to get my image. So let's see. If I take -2 and multiply it by 2, what do I get? -4. -2 times 2 is -4. What is 1 times 2? 2. What is -1 times 2? -2. What is 0 times 2? What is 2 times 2? 4. So I could have chosen any point and any coordinate, and it's going to work. The only one it doesn't work with right here is 0, just because 0 times 0 is 0. So if you see zeros, don't use it, but it will work for every other one. When you multiply the scale factor and you're fine, but don't actually use the zeros to find scale factor. Do you see what we did there? Yeah? Kind of?